Okay, so we've established that the x vector over here, and we'll do an x vector in the row space of A. The x vector over here that maps to the vector AX over here that's closest to the B vector requires that this AX vector be the projection of B along the direction of the null space. So that this vector AX minus B is minimized. In other words, the vector AX is closest to B, so this distance here is minimized if AX minus B is in the null space. Which means that AX minus, well, here we have it. Our condition then is that AX minus B is in the null space of A transpose. So, AX minus B in the null space of A transpose. What does that mean? That means that A transpose times AX minus B is 0. That's condition for a null space. We're in the null space if that matrix maps this thing to 0. Well, that algebraically is very simple to first of all simplify and then write is this. B extend up there, almost looks like a T with the arrow, okay. That A transpose times AX has to equal A transpose B. This is all just very simple, okay? I mean, reasoning all this out is anything but simple. This is very challenging and complex reasoning at the level of a very introductory linear algebra course, okay? So this is not trivial reasoning, it's not a trivial picture, it's a very profound and important picture, but once we've established that this is the condition, that AX minus B has to be in the null space of A transpose, that means again that A transpose multiplied by X minus B is a 0 vector, which is obvious, and then it's just two simple algebraic steps to get this, and this gives us a system of equations to solve for the vector X. And this is the key to finding the regression function, which allows us to, for example, do the depth versus clock time model, if we know what that is, according to 5 given data points, and accounting for all those data points as opposed to just picking 3 points and doing a quadratic model. And we'll address that next.